Welcome to Maths with EJD, and I continue with the videos on scientific computing with Python. So first of all, I share my screen. Afterwards, I find my way to where I can launch Jupyter Notebook, and then the command line thing comes up, and then afterwards, a web page shows, which is a local web, so to speak. And then when it loads, I navigate to the desktop and then I go to the folder containing scientific computing with Python. And in this video, the focus is on broadcasting in NumPy, broadcasting in NumPy. If you if you are new to this channel or this is your first video on this, I have a couple of videos. This is the 12th video, in fact, on scientific computing with Python, apart from the videos on mathematics and other and different topics in maths like that. Yes, and for this, right, because I believe in hands-on learning of coding, programming, and things like that. So I have made the notes available so you can check the description box. So you click on that and you can download all the notes and then follow along in this journey. So today, the focus is on broadcasting in NumPy, and you need to understand that broadcasting in NumPy is a powerful mechanism that allows NumPy to perform operations on arrays of different shapes in a way that would not be possible otherwise. Now, you already know by now that NumPy is numerical Python, and it is very strong with arrays, matrices, like that. So, and of course, broadcasting in NumPy simplifies arithmetic operations on arrays of different shapes, making code more efficient and readable by eliminating the need for explicit looping and array resizing. So instead of having to loop, you don't need that. I think there was a previous video I made on Python control flows that we talked about looping using using for loops and the other loop is trying to remember now. Okay, I mean that's not coming right now. So understanding and leveraging broadcasting can significantly improve performance in numerical computations. So broadcasting follows a set of rules to make array shapes compatible for arithmetic operations without needing to explicitly replicate data. So let's talk about some rules of broadcasting. So the whole idea of broadcasting is doing something over an array. So for instance, one of the broadcasting rules will be matching dimensions. If the arrays differ in their number of dimensions, the shape of the one with fewer dimensions is padded with ones on its left side. Now that may sound abstract, but you can see an example would be that if you have a shape which is 3 by something that is not specified, so that it is automatically treated as a 1 by 3 array when being broadcast against a 3 by 3 array. You see the left side, is 3, right? So the 1 is now taken to the left of it, right? So if the other part is not specified. Then we also talk about size compatibility. So arrays are compatible in a dimension if they have the same size or if one of them has size 1. For instance, if you have a 4 by 1 array, it can be broadcast with a 4 by 3 array. So because they have the same size, like that. Then you can talk about resulting shape. What shape results when you do some of these operations? The resulting array shape is the maximum size in each dimension of the input arrays. So if you do like a 4 by 2 against if you do a 4 by 2 against a 3 by 4, so you can be sure, 4 by 2, 4, 2, 3, 4. So the bigger array is what you're going to end up with a 4 by 4 like that. So because the resulting array shape is the maximum size in each dimension. So the highest number of columns and the highest number of rows is what you end up getting like that. Okay, so we talk about broadcasting examples, some basic examples of broadcasting. So for instance, you can add a scalar to an array. You can add a scalar to an array. So you have an array, you just want to add the same scalar number to it. So that's part of that's like what broadcasting is about. So you are doing same thing all over the whole array. So adding a scalar to an array adds the scalar to each element of the array. For instance, of course, since you are dealing with NumPy, so you have to import NumPy as NP, and you declare an array. So from a Python list, you make a NumPy array, and then B is a scalar, which is 2, and then you want A plus B. That means to this array, you're adding 2. That means you're adding 2 to each element in the array. So that means by the time you run this, you have 3, 4, 5. That's 2 plus 1, 3, 2 plus 2, 4, 2 plus 3, 5. That's adding a scalar to an array. Then another thing is you want to add arrays with compatible shapes. Arrays with compatible shapes. For instance, you have an array A, which is a 3x1 array. That's 3 rows, uh, 3 rows and 1 column. The way it is defined, right? Um, to make something into a matrix form, right? This is like an array of arrays, except that it is a list of lists rather, and then each list contains just one element. So by making it a list of lists, you say it's going to be a 3 row, 1 column thing. And of course, this other one is a 1x3 because it's just the numbers listed in one list like that. So you have 3x1, 1x3. So just like you know already, so you have 3 rows, 1 column, and 1 column, 3 rows. So by the time you broadcast everything together, you're going to end up having the highest number of column, which is 3, and the highest number of row, which is also 3, is going to be what everything is going to look like. And if you run this, see what that gives. So 11, 21, 31, 12, 22, 32, 13, 23, 33. And what exactly is happening is that you add 1 to everything, you have 11, 21, 31. Add 2 to everything, you have the second row. Add 3 to everything, you have the third row. And that's exactly what's happening right there. So adding arrays with compatible shapes. Now, what about broadcasting with higher dimensions? Broadcasting with higher dimensions. So in this case now, you have an array. You have like this is okay. First of all, you have a list of lists. So this is like on its own, this is going to be like a 3x1, and then this is going to be like another 3x1, and then you have two of that. So it's like you have 3x1 in two places. That is why the shape of this is like 2 3x1, 2 3x1. That's what this means. So 3x1 in two places. So you have 2 by 3 by 1, and then the B now is NP array. That's 10, 20, 30. That's just it. That's a 1x3 thing. So just like the way it is, you have 1x3. So if you add A plus B, of course, like you know already. So it means you're going to have, 1, 2, 3 added to this whole thing, and then 4, 5, 6 added to this whole thing. So it's like you're going to have 3x1, 3x3 in two places, just like you have 3x1 in two places there. So if you run this, see what you get. Okay. So what's happening is you have you are adding 1 to everything. That's 11, 21, 31. Add 2 to everything, 12, 22, 32. Add 3 to everything, you have 13, 23, 33. Then you do the same, 4, 5, 6 by this. So this 2 times, so this like at the end of the day, the result is 2 by 3 by 3. That means you have 3 by 3 in two places, because you can see that, being covered up. So this is like 1, and this is 2. So that's broadcasting with higher dimensions. You can also do element-wise multiplication with different dimensions. Element-wise multiplication with different dimensions. For instance, here you have a 2 by 3 matrix. So this is row 1, row 2, and then 3 columns in each case. That's 2 by 3. And then you have this 1 by 3 stuff. So 1 row, 3 columns. And then you want to do a 2D array, and a 1D array can be broadcast for element-wise multiplication. So if you have A star B now, that's 1 times 10, 10, 2 times 10, 2 times 20, 40, 3 times 30, 90, then 4 by 10. So you can have that too. That doesn't just work for only addition. All right. So you can also talk about broadcasting in more complex scenarios. So imagine that you have a 4 by 3 by 2. You have a 4 by 3 by 2 shape, and then you want to add that to a 3 by 2. Now, for you to really understand this, okay, right now we are just focused on the shape, but I want to show what exactly the elements are here. So you want to print A, then I put a blank print for you to see what's happening. Print blank, and then you have B again. Print, so you want to print B itself, and then we come again and print blank, so we can have some space. And then here you actually want to print the result, right? So print result, then of course print blank, and then you want to print the shape so you can see what it looks like. So see what all of that is. So it's all this lengthy stuff. First of all, if you print it, it's a 4 by 3 by 2. So it means you have 3 by 2 in 4 places. So you can see this is 3 rows, 2 columns in 1, 2, 3, 4 places. That's the first one. The second one is just 3 by 2. So the first one is 3 by 2 in 4 places. That's 3 by 2 1, 3 by 2 2, 3 by 2 3, 3 by 2 4. That goes. Then the next one is 3 by 2, just 3 by 2 in one place. So you have, apart from that 4, you just have this 3 by 2, and that goes. So the next thing you're printing is result of A plus B. So if you do the result of A plus B, you already know that the result of A plus B, well, to be sure of that, let me do something like this so we can know where that is. So you can say the result of A plus B is, then comma, result, something like this. Yeah, so yeah, this is exactly where the result of A plus B is. So it's actually you adding this B, this 3 by 2, you're adding it to this other place. So it means that this B now, this B, which just appears only once. Okay, let me go here too and say the result of B so that we can actually see. Okay, let me just do this. Okay, but here this has to be like A is, we say A is, comma A. Then here we say B is, comma B. And the result is this. So we have this. All right. So the A is this, B is that, the result of A plus B. So it's like A, you're adding this B to each, you're adding B to each of these cases. So that means that the result of A plus B is just going to be 0.001 something something added to this 0.9192 blah blah blah, like that. So you also add this one to that way. So you can see 0.001 this. If you add this to this, you get 0.9144. So then if you add 0.57 to 0.64, that's why you have 1.22. And you do that across. So that's also going to give, so that's now going to end up giving you the 4 by 3 by 2. And that is why the shape of the addition, which we are interested in at the end of the day, is print result.shape. You have 4 by 3 by 2, like that. Okay. So let's talk about some practical applications in this case. For instance, you want to normalize data. Now, normalization of data is something that happens a lot when in data analysis and machine learning. So we get to normalize data so that we can easily work with the data. So one of the practical application of broadcasting is in normalizing data. For instance, you want to normalize a matrix by subtracting the mean and divide by the standard deviation. That's a very good way. I mean, this is a standard practice in statistics, right? When you want to get you have a test score and you want to normalize it. So you can use broadcasting to do that and see what's happening. You have a list of lists, so which is going to give you a two-dimensional array. That's 2 rows, 3 columns. And then you want to find the mean of all that. You want to find the standard deviation of all that. And the normalized stuff is now the mean minus the mean, I mean the value itself, which is 1, 2, 3, and then x minus x mean. So each x subtracted from the mean, or mean subtracted from the x divided by the standard deviation. Then you can now print the normalized value, and that's exactly what you have here. Okay, so of course you may want to visualize all that. So you may want to see print x underscore mean, print x underscore mean. Of course, you want to separate that so you can see clearly. And you also want to print x underscore std, x underscore std, and then you also want to print that like this. And then of course the normalized thing now comes, so you know what's happening. So you can see that the mean, so you have the mean here is 2.5 and the mean here is, okay, so it's like the mean 1 plus 5, so 1 plus 2 divided by 2, 2.5, 2 plus 3 divided by 2, no, yeah, that's axis 0. What's happening here? So it's like 1 plus 5, 1 plus 4, 5 divided by 2, 2.5, then 2 plus 5, 7 divided, yeah. So because axis 0 now, so it's like 1 plus 4, 5 divided by 2, 2.5, 2 plus 5, 7 divided by 2, 3.5, 3 plus 6, 9, 4.5. So the mean across board now is, so the mean in axis 0, the mean of everything is now 1 0.5. If you add everything together, that's like adding from 1 to 6. That's 6 times 742 divided by 6. That is no, that's not working. The mean. Okay, yeah. So the standard deviation now, sorry, is this 1.5 all the way. And then if you subtract and divide, you end up getting all these normalized numbers. So normalization helps you to operate with the set of data you have. And the axis also matters. For instance, if you change the axis, let's say you bring this, if you now change the axis, so you want to do it in axis 1, and then this also is in axis 1. The values also change. So you can see, okay, this doesn't work down the way, so it's better we avoid it. Okay, this doesn't work all the way. Okay, axis 0 only is what works here. So we go to vectorized operations. Vectorized operations. So broadcasting allows for efficient vectorized operations without explicit loops. For instance, you define your X to be a list of lists also. That's a two rows, 3 column thing. So you have that. And then of course you now have a 1 by 3 stuff too. So the weighted sum will now be this X multiplied by W. So if you print the weighted sum, see what you get. So it's more like you have 0.2 times 1, that. Then you have 0.5 times 2, that's 1. 0.3 times 2, that's 0.9. Then you have 0.2 times 4, 0.8. 0.5 times 4, that's 2.5. 0.3 times 6, that's 1.8. And with that, we come to the end of broadcasting in NumPy. So if you have not subscribed, be sure to do that. Hit the notification bell also, so you can get alerted each time a new video is released. In the next video, I'll be talking about advanced broadcasting. So that's to, maybe some higher things you can do with broadcasting. So don't also forget to comment, like, and share. Thank you so much for listening. See you in the next video.